Elementary row operation is an operation that transforms the equation system into a simpler form, but keeps the solution set the same. There are three such elementary row operations. We can exchange two rows, we can multiply an equation by a non-zero constant, or we can add two equations. We're going to demonstrate these elementary row operations in an example. You want to solve the system equation of equations given by 3x plus 4y equals 14, 5x minus y equals 8. We first begin by writing this as an augmented matrix, 3, 4, 14, 5, negative 1, 8. Now we're going to perform elementary row operations until we reduce this matrix to row echelon form. The first thing that we're going to do is we're going to multiply row 1 by a third. The reason we want to do this is because we want to get the entry in the 1, 1 spot from a 3 to a 1. So dividing row 1 by 3 will accomplish that. So row 2 remains the same, and row 1 becomes 1, 4 thirds, and 14 thirds. Next, we need to eliminate the 5 in the first column, second row. We do that by taking negative 5 times row 1 and adding that to row 2. So negative 5 times 1 is negative 5, plus 5 is 0. 4 thirds times negative 5 is negative 20 thirds, minus 1 is negative 23 thirds. 14 thirds times negative 5 is negative 70 thirds, plus 8 is negative 46 over 3. So our last row becomes 0, negative 23 over 3, negative 46 over 3. The next step is to get the entry in the second row, second column spot to be a 1. We can accomplish this by multiplying row 2 by negative 3 over 23. And of course, negative 23 over 3 times negative 3 over 23 is 1. Negative 46 over 3 times negative 3 over 23 is 2. Now we have the system of equations in a form that we can solve. Our bottom row can be read 0x1 plus 1x2 equals 2. So we know that x2 is equal to 2, or y is equal to 2. But if we take row 1 and add to it negative 4 thirds row 2, we can actually reduce this to what's referred to as reduced row echelon form. So if we do that, we get 1 plus negative 4 thirds times 0, 4 thirds plus negative 4 thirds times 1, and that's equal to 0. And we get 14 over 3 plus negative 4 thirds times 2. That gives us 2. So you can read straight off that x plus 0y equals 2, and 0x plus 1y equals 2. So x is 2 and y is 2. This is said to be in row echelon form if all rows that contain only zeros are at the bottom of the matrix. Correspondingly, all rows that contain at least one non-zero element are on top of rows that contain only zeros. Looking at non-zero rows only, the first non-zero number from the left, called the pivot, is always strictly to the right of the pivot of the row above it. Variables corresponding to the pivots in the row echelon form are called basic variables, and the others are called free variables. A system of equations is in reduced row echelon form if it is in row echelon form, if every pivot is 1, and the pivot is the only non-zero entry in the column. Here's an example that's been put into row echelon form. Our pivots are in row 1, column 1, and row 2, column 3, meaning column 2 and column 4 are free variables. Looking at the equations given by this matrix, we have x1 minus x2 plus 2x4 equals 4, or that x1 is equal to x2 minus 2x4 plus 4. Our second row corresponds to the equation x3 minus 3x4 equals 7, or that x3 is equal to 3x4 plus 7. Given that x2 and x4 are free variables, we can call them s and t respectively. Then for any real numbers, s and t, x1 is equal to s minus 2t plus 4. x2 equals s, x3 equals 3t plus 7, and x4 is equal to t. Here's a bit of a quick trick to solve the equation ax equals 0. We can quickly find the solution by taking a and putting it into row echelon form. In any row that there is no 1 on the main diagonal, add a row into the matrix that looks like a bunch of zeros, a negative 1 on the main diagonal, and then zeros everywhere else. This turns our matrix A into a square matrix. The solution to ax equals 0 is given as a linear combination of the columns where the main diagonal value is negative 1. We illustrate the negative 1 trick with this example. We've taken a matrix A and we've reduced it to row echelon form. We notice here that column 2 doesn't have a 1 on the main diagonal, and column 5 doesn't have a 1 on the main diagonal. So we're going to insert rows in row 2 and row 5. So our new matrix A tilde has a new second row, 0, negative 1, 0, 0, 0, and a new final row, 0, 0, 0, 0, negative 1. So the solution here is given by x is equal to s times the vector 3, negative 1, 0, 0, 0, plus t times the vector 3, 0, 9, negative 4, negative 1. In our next video, we'll show how matrices play a role in vector spaces.